my dear students. I hope you all are happy and healthy. This is Seema Banjare, your mentor. Once again, I welcome you in part 2 of number systems. As you already know from thumbnail that this video is about, it is a successor video on number systems. Let me tell you what all we will discuss here. So the first thing that we will be discussing is decimal expansion of real numbers, and then we will move on to discuss operations on real numbers. While discussing all these concepts, we will solve one or the other questions here and there just to make things more easy to understand. Okay, so let's start today's class, right? If you remember, in previous video I told you that the exact difference between rational and irrational numbers we will make it clear in the next video, right? So it's here where we are going to make the difference really clear, that what is the exact difference between rational and irrational numbers. But before we do that, I want you all to do a small activity with me. Okay, so be with me. So we are taking 3 cases. So case 1, case 2, case 3. So the case 1 is 99 divided by 4. Okay, case 2 is this number 10 divided by 3, and case 3rd is this number root 2, right? So what 99 upon 4? 99 upon 4 means 99 divided by 4. And when you divide 99 by 4, what do you get? So 4, 2 times 8, 1. You already know division. Okay, so 4 times 16, 3, and then we will bring 0 down. It wasn't there, so we will add a decimal point. So 4, 7, 28, and then again 2, and then 0. I'm not teaching you division. Don't think that I'm teaching you division in 9th standard. No, not at all. So 4, 5 times is 20. Okay, so you see, so when we were solving it, at this point the remainder has reduced to 0, right? Reduced to 0. The division has come to an end, or we can say the division has terminated, right? So such numbers like 99 upon 4, when we divide them, the remainder becomes 0. So such cases, the number is known as terminating numbers, right? Because the remainder at some point terminated to 0, it reduced to 0, right? Let's see the second case, 10 upon 3. So 10 upon 3 means 10 divided by 3. So 3 times 9, we are left with only 1, and there is nothing. So we will bring down 0, and once we bring down 0, we'll add a decimal. So again 3 times 9, then 1, we'll again bring down a 0. We will add 3 here, then 3 times 3 is 9, then 1, and this process, you see, this process will keep going and going and going in. So it will keep going on. So such kind of cases where the decimal is not getting reduced to 0 and the division is it's going on and going on. So such cases are known as non-terminating, because it's not getting terminated. It's non-terminating, but it is repeating. As you see, the decimal expansion is getting repeated, 3.3333 and so on. So this is non-terminating, but it's repeating. So if I ask you, decimal expansion of 99 upon 4 was terminating, decimal expansion of 10 upon 3 was non-terminating but repeating, right? Now let's come to root 2. What root 2? Now if I'm not wrong, you already know how we can find out decimal expansion of root 2, because you have already done this thing in your previous classes. Maybe in 8th class you have done this, but still here we will touch upon this. So root 2, okay? In order to find out the decimal expansion of root 2, we try to take numbers in pairs by pair. What I mean, if I'm taking 1 as, let's say if I'm taking 2 as divisor, I need to make 2 as the quotient. So 2 times is 4, but I cannot take 4 because in that case the 4 becomes greater than 2. So I cannot take 2 times 2. So I need to take a smaller number. So what is smaller than 1? It is a 1, right? So the integral number that is less than 2 is 1. So I take 1. So 1 times 1 is 1. So it works, right? 1 times 1 is 1. So the remainder is 1 here. Now still the decimal, the division is not complete. There is scope for decimal expansion. We will bring down 2 zeros and we will bring down zeros in pairs. So this you know that while solving these root numbers, we always bring down, after decimal numbers or zeros in pairs. So we will bring down a pair of zeros. So 2 0. Now this 1 plus 1, this 1 plus 1 will be 2. And now we have to decide upon the second number. So this number we have to decide that what we are going to take here. So let's say if I take 1 here, so 21. So this number is 21 times, point here. So 21 times 1 is 21, which is way too less than 100. So we cannot take 1 also. Okay, if I take 2, so what it becomes? 22 times 2 is what? 44. And 44 is also, less than 100. There is scope for some greater number. So what will fit here? 4 will fit here, right? 4 will fit here because 24 4 times will be 96. So we'll take this 96, and 100 minus 96 is what? 4. Okay, so 4, and again it's not complete. We'll bring down 2 more zeros, a pair of zeros once again, and now 24 plus 4 is 28. And now we have to decide upon the third digit here. So 281 times will be 281, and now there is no scope for any greater number, because if we take 282, the 282 2 times will become greater than 400. So we cannot go for that. So we need to suffice with this. 281, 1 times is 281, and the remainder will be 0 minus 1 9, and 1 1 and 1 190, right? Again we'll bring down 2 zeros because it's still not complete. Now 281, 1 times we'll add it, 282, 1 plus 1. Okay, you're getting what I'm doing? 1 plus 1. So 281 plus 1 is 282, and now we have to decide upon the next digit. So what will come here? I know 4 will come here. You do it, try and test it again and again. 2824. So 4 times 4. So 4 4 16, 1 4 8 plus 1 is 9. 4 32, 32, 32 3, 8 1. Okay, so now 4, then this 0, right? And what? 6. Is it correct or not? 0, 10 minus 0, then what's here? Okay, it's 8 minus, this is correct, right? Okay, basically what the idea is that at this point also the decimal, this number has not terminated at any point, and if you will do this division, if you will continue doing this division, right, what you will find? You'll find that this decimal expansion keeps on going on. It keeps going on, and so it keeps going on, and no number, nothing gets repeated. So such numbers wherein, because it's too tedious to solve here, right? You can see. So if you want to see it, you can see it for yourself, but I don't want to do it. That's for no reason. So you see that this decimal expansion will be, it won't get repeated, and it's not getting terminated at all. So such numbers are non-terminating, neither they are getting terminated, non-terminating also, and non-repeating. You see it? Okay, now let's see the difference. 99.4, what kind of number it is? It is a rational number which terminates. 10/3, what kind of number it is? It is a rational number which doesn't get terminate but it gets repeated. But root 2, it neither gets terminated nor gets repeated. So I think the difference is clear to you. Okay. Yeah. So rational numbers, let's once again take this difference here. Rational numbers and irrational numbers. So these two numbers, 99/4 and 10/3, these are rational numbers. So rational numbers are the numbers that are either terminating, or if they are not terminating, then they are getting repeated. Okay, so if a number is terminating, it is a rational number. If it is non-terminating but repeating, then also it is a rational number. But if a number is non-terminating and non-repeating, then it is an irrational number. Okay, so the difference is clear.
Alright, let's sum up. The decimal expansion of rational numbers will always be terminating or non-terminating but repeating, whereas the decimal expansion of irrational numbers will always be non-terminating and non-repeating.
Now I want you to tell me what kind of number pi is, whether it's a rational number or it's an irrational number. So in the previous video, I gave you some examples of irrational number, right? I told you that root 2, root 3, root 5 and pi, root 7 are irrational numbers, right? So pi is an irrational number, right? So pi is an irrational number, but 22/7 is a rational number. Okay, but how come it is possible? Because pi is irrational and 22/7 is rational, and 22/7 is nothing but the value of pi. So if pi is irrational, how come 22/7 be a rational number? Okay, so this is a question for you. If pi is rational, then why 22/7 is rational? So this you have to answer in the comment section, right? For now, we are moving ahead. So now we'll take some questions so that this particular concept, decimal expansion of real numbers, becomes more easy, or it becomes easy for you to understand, right? Or we are just saying the application of it. Okay. So let's take some examples. 3.4, what kind of number it is? You see, it's only 3.4. It's not going on and on. So how do you know it's not terminating? If it is like 3.4 ... it means so on. It means the division is not coming to an end, right? So if the dots are there, if it's only 3.4, right, it means it's complete. Yeah, so it is a rational number, right? If I say 5.2222 and so on, so this division is not it's not getting terminated, but it is getting repeated. So if it is getting repeated, in that case also it is a rational number. Let's take another example. What about 4.16231571 and so on? So you see that this decimal expansion is not coming to an end at all, because the dots are there, and these numbers are not, any of these numbers is getting repeated. So it's non-terminating and non-repeating. So what kind of number it is? It is a rational number. So this is how you can identify like whether a number is rational or not. Clear? Okay, now if I ask you, express this in P/Q form, you will surely be able to do this, because as you see that this is non-terminating, okay, and it's terminating because there is no dot there. So it means it terminates. Okay, you can express it in a P upon Q form because this is a rational number, and you can surely express this in P upon Q form. So how do we do this? We remove the decimal from here and bring down zeros. It becomes, and now you can, cut it and bring it in the lowest form. So it becomes 109 upon 20. So this is how you can do it, how you can bring it in P upon Q form. But if I ask you, express 3.444 and so on in P upon Q form. Okay, now there is a challenge because 4 is getting repeated. Okay, and we have to express it in P upon Q form. How we are going to do this? Let's see. Okay, this is 3.44 and so on. We can also write this as 3.4 bar. So many a times if it is written that express 3.4 bar in P upon Q form, it's nothing but 3.44 and so on. So if it is there is a bar on one digit, it means that digit is getting repeated. If the bar is on 2 digits, it means those 2 particular digits are getting repeated. So here, first what we will do, we will suppose that this number is x. So let us consider that x is equal to 3.44 and so on. And let's say this is equation number 1. Now, so how many digits are getting repeated? One digit is getting repeated. It means we will multiply this equation by 10. If 2 digits are getting repeated, we will multiply it by 100. If 3 digits are getting repeated, we will multiply it by 1000. So in this case, we will be multiplying equation number 1 by 10, and by that we will get 10x is equal to, if you multiply the RHS with 10, what you will get? You will remove the decimal from here and it becomes, it means like if you multiply it by 10, decimal will shift 1 point forward. So 34.44 and so on. Let's say this is equation number 2. So this is equation number 1 and this is equation number 2. Now the next step is subtract equation number 1 from equation number 2, and when we do this, 10x minus x will get 9x, and this minus this, okay, let's see here how we do it. So this 34.44 and so on minus 3.44 and so on. So 4 will cancel out, and 4 minus 3 is 1 and then 3. So what it is? 31. X is equal to 31 upon 9, and we need not to cut it. Even if you want to, we cannot, because it is already in its lowest form. So the value of x is 31 upon 9, and x was nothing but 3.4 bar. So the P upon Q value of this is 31 upon 9. Okay. So this was one of the examples, and similarly you can solve many other questions. If likewise I said if 2 digits are getting repeated, you just need to multiply the equation by 100. If 3 digits are getting repeated, multiply it by 1000, and the the further steps will remain same. Okay, we will be solving more questions on this particular concept in the next video, which will be totally dedicated to questions from this chapter. For now, let's move towards our next concept, which is operations on real numbers. Okay, so now when we say operations on real numbers, okay, operations on real numbers, operations, what does we mean? So basically there are many operations in mathematics, but there are 4 basic operations, and these are the basic operations: addition, subtraction, multiplication and division. These are the basic mathematical operations. So if we perform any of these operations on real numbers, how they are going to react. Okay, if a rational number is operated, and by operation I mean any of the operations, addition, subtraction, multiplication, division, anything. If a rational number is operated with a rational number, okay, if any of these operations is being performed between a rational and rational number, what will be the result? The result will be a rational number. Okay, so if any of these operations is being performed between rational numbers, then the result will be a rational number. Let's take an example, because examples generally makes the things more clear. Okay, so here let's take any rational number, let's say 2, and another rational number, let's say 3 upon 4. So if I multiply these two numbers, what will I get? I'll get 3 upon 2, which is again a rational number. So this is simple, right? What if any of these operations is being performed between a rational and irrational number? How they are going to interact? We will get an irrational number. And for example, let's say if 2 is added to root 3, okay, so it will be, the result will be an irrational number. If any of these operations is being performed between a rational and irrational number, if one number is rational, another is irrational, then the result will be an irrational number. So 2 is rational, but root 3 is an irrational number, and their addition will result into an irrational number. Okay, so 3 root 5, what is happening here? 3 is a rational number, but root 5 is an irrational number, and when we multiply these two numbers, 3 multiplied by root 5, that is 3 root 5, it becomes an irrational number. Okay, am I clear? Even if not, you cannot say. Okay, now if we perform any of these operations between irrational numbers, okay, if both the numbers are irrational numbers and we are performing any of these operations, be it addition, subtraction, multiplication or division, if we perform any of these operations, then the result will be, it will either be a rational number or an irrational number. Okay, so how? So we will try to understand this case. Okay, let's say I multiply root 2 is an irrational number. If I multiply root 2 and root 2, what will I get? I'll get 2, because root 2 into root 2 is 2. Root 3 into root 3 is 3. Root 4 into root 4 is basically 2. If I say root 5 into root 5, 5. So root 2 into root 2 is 2. Okay, so this is a rational number. So irrational on multiplication gives you a rational number. But if it is a root 2 plus a root 5, you will surely get an irrational number. You can add on these values and you can just see the answer for yourself. So the answer will be an irrational number. Okay.
Well, the gist is clear. Rational meets rational to give a rational number. Rational meets irrational to give an irrational number. And irrational number meets an irrational number to give either a rational number or an irrational number.
Okay, my dear students, so we have discussed operation on real numbers, and we have seen like how these operations react when like how rational irrational numbers react when any of these operations is being performed on them. You know that in your book there is an entire exercise given after this concept, and that exercise the questions are basically to simplify. You just need to simplify the expressions. Okay, and to solve that exercise they have given you certain formulas to cram, and then on the basis of those formulas you have to solve the exercise. I'll be pasting a snippet of those formulas here on the screen, but I will not advise you to learn them, to cram them, because that would be of no use. Instead, I would advise you to learn these basic algebraic identities, because these are of more use, like in future also, and like they'll be of more, they are more purposeful basically. So the first algebraic identity is x plus y square. So this is x square plus y square plus 2xy. X minus y square, x square minus 2xy plus y square. And when x plus y multiplied by x minus y, so it simply becomes x square minus y square. Okay. So these identities you have to remember, you have to mug them up. Okay. So where we are going to use these identities, so let's take an example. Okay, if I say do this, okay, simplify this expression. Okay, you just need to see like what identity it resembles to. So 3 root 3 plus root 5 root 3 minus root 5, you can see that it resembles to this identity, x plus y, x minus y. So x and y. So the answer is x square minus y square. So there we can use these identities easily, right? So it will become root 3. So x square means root 3 square minus y square, that is root 5 square. So root 3 square is 3, root 5 square will be 5. So the answer is minus 2. Okay. So this is how we can simplify these expressions using these identities. So there will be some cases wherein you will feel that no identity is getting fit in this situation. So what do we do in that scenario? You can simply move ahead with simple multiplication that you know, and you will get the answer, right? Okay.
Well, that's all for today. Let's quickly summarize whatever we have discussed in today's class.
Alright, my dear students, so we have come to an end. I don't want this video to be more lengthy, so let's wrap it up here. We'll see you in the next video. But before going, I just want you to I just want to request you all, please don't forget to like, share and subscribe to the channel. Bye bye, take care.